All right, so today we're going to finish up section P5, section P5, where we're going to learn how to add and subtract rational expressions. So before we get to that, I did want to address something from the first quiz that I saw a lot of people doing, and I just wanted to quickly address it, and we can move on to finishing P5. So remark from quiz 1. So on the quiz, there was a question something like this. Looks something similar to this. And what some of you did, the first mistake was that you distributed the exponent 4 to the number 2 out front. So you wrote something like this. And the reason that's wrong is because the exponent 4 here is only on the x squared times y to the negative 3. It's not on the 2. So there's no reason for the 2 to get the exponent. Okay, and on the same problem, if you didn't make that mistake, the other mistake was after we distributed the exponent correctly to x squared and y to the negative 3, it was at this point that I saw a lot of you distribute then, parentheses are on this, distribute then the 2 to each of the factors inside. So it was something like this. And so this again is wrong, and the reason is we don't distribute across multiplication, but only across addition. So I'll give you an example to illustrate what I mean. So we don't distribute in that case. Now why? So if it was something that looked like 2 times x squared plus y, then we do distribute the 2 across the multiplication. This is okay. So we get 2x squared plus 2y. This is fine. But when it's something of the form 2x squared, 2 times x squared times y, we don't distribute. This simply becomes 2 times x squared times y. And a reason that we don't distribute can be seen from an example using numbers. Remember, we view the variables x and y as some arbitrary numbers. And so let's look at if we were to do 2 times 3 squared times 4, let's say. So this looks very similar to the 2 times x squared times y, where x is 3 and y is 4. If we were to distribute, we would get the wrong answer. So let's compute this the right way and see what the answer is. So this is going to be 2 times 9 times 4, which is 2 times 36, which is 72. So this is the right answer. So now let's see what would happen if we distribute the 2 to the 3 squared and the 4. So let's say we did, okay, so this is 2 distributed to the 3 squared, and then we still have 2 distributed to the 4. This would be 2 times 9 times 8. Right, so this would be 2 times 72, which is 144. So these are not the same thing And we know that the right answer is 72. So be aware that you can only distribute across addition. Okay. Now, from last time, we went over how to multiply and divide rational expressions. So we first factored everything, and then we multiplied the numerators together and the denominators together, just like when we multiplied fractions of just numbers together. And then in the end, we canceled out like terms, common factors of the numerator and denominator. So now, with addition and subtraction of rational expressions, it is very similar to the way that we add and subtract rational numbers. So addition and subtraction of rational expressions. All right. So let's jump right into an example. Now, just like with adding and subtracting fractions of real numbers, adding and subtracting rational numbers, if there is a common denominator at the beginning, then we can just add the numerators together and we're done. So in this example, we have the exact same denominator, which means we don't need to worry about finding a least common denominator or changing either of the fractions. We can just go right into combining the numerator and denominator. So this is 3x minus 2 minus quantity. This is important. The parentheses here are very important. 2x minus 1 all over x squared minus 5x plus 6. And so we have 3x minus 2 minus, so I'm going to distribute the negative 1 out front of 2x minus 1 to both the 2x and the negative 1. So this becomes minus 2x plus 1. And finally, we can simplify the numerator by combining like terms. So we have a 3x and a negative 2x becomes an x. We have a negative 2 plus 1, so negative 1. Okay. So that's just one example. I think it's pretty straightforward. We have the same denominators. So we can just combine the numerators and we're done. Now, notice that in this problem, we can factor the denominator. So we have two factors of 6, namely negative 3 and negative 2, that multiply to 6 and add to negative 5. So this factors as x minus 3 and x minus 2. And I just did that just so that we can remember to get into the habit of factoring things just in case we are able to cancel with something in the numerator. Now in this case, we only have an x minus 1 in the numerator, which doesn't cancel with either x minus 3 and x minus 2, but in future problems, we may get to the end here and see that we can still factor and cancel some terms. Okay, so let's jump right into finding a least common denominator of two rational expressions. Because we're going to need to know how to do that when we add expressions that don't have the same denominator. So finding a LCD, or least common denominator, of two rational expressions. Okay. So let's go over the steps, and then we're going to go into some examples. So the first step is to factor the denominators involved. Denominator. Second step is to form a product. This one's a little bit tricky, but we're going to form a product of the distinct factors that appear. Of the distinct factors that appear. And so, of course, an example will illustrate exactly what we mean by this. So we're going to form a product of the distinct factors that appear. That appear in the factorization of each of the denominators, of course. So the final step is to raise each factor from the second step to the greatest power that appears in either denominator. Okay? So as an example, let's jump into the first one. We have 3 over x squared minus 1. We're going to add that rational expression to x over x squared plus 2x plus 1. So let's find an LCD. We're going to add these two fractions, and we realize they do not have the same denominator, so we need to find an LCD. Step 1 is to factor each denominator. So the first denominator is x squared minus 1. We notice that that is a difference of squares, which factors as x minus 1 times x plus 1. And we factor the trinomial x squared plus 2x plus 1 as x plus 1 times x plus 1, which we rewrite as x plus 1 quantity squared. Okay, so step 2, again, is to form a product of the distinct factors that appear. So what are the distinct factors that appear anywhere in either of the denominators? So the factor x minus 1 appears, and the factor x plus 1 appears in the first one. The factors that appear in the second one, in the second denominator, is x plus 1. I've already written it down there, so I'm not going to write it again. So number 2 here is a list of all the distinct factors that appear anywhere in either denominator. And finally, I'm going to look at number 2 and raise each factor to the greatest power that appears on that factor in either denominator. So, for example, let's look at x minus 1. I'm going to raise this to a power. Now, what power am I going to raise it to? Well, x minus 1 only appears in the first denominator, and so the highest power that x minus 1 appears in either is just 1, so that gets left alone. Now let's look at x plus 1. So x plus 1 appears in both denominators, but in the second denominator, it appears to the second power, and that's the highest power which it appears. So our LCD is x minus 1 times the quantity x plus 1 squared. And so the next step is, again, similar to what we do when adding two rational numbers, two fractions of just numbers with no variables. We are going to multiply the first fraction by a fancy number 1. We're going to multiply it by 1 in a fancy way so that the denominator of the first fraction matches our LCD. So let's change 3 over x squared minus 1, which is 3 over x minus 1, x plus 1. So how far away is the denominator here from our LCD that we found here in step 3? Well, it's missing a factor of x plus 1. So I'm going to multiply both the numerator and denominator by x plus 1. Really, I'm just multiplying it by 1. So here I get 3x plus 3. And in the bottom I get, well, I should get the LCD. And similarly, I'm going to change the second fraction by multiplying it by whatever I need to make the denominator the LCD. And in this case, I only need to multiply by x minus 1. So in the top, I have x squared minus x, and in the denominator, I have, again, hopefully it's the LCD. Okay, so what I've done at this step is change each fraction in the problem by multiplying it by 1, so that now each fraction is the same as it was, since we multiplied by 1, but they have a common denominator, which means we can now combine their numerators. So we have, finally, 3 over x minus 1 times x plus 1 plus x over x plus 1 squared, this is the original problem, equals, let's use the new version of the first fraction, and add that to the new version of the second fraction. And now we can simplify the numerators. So here we have x squared, we have a 3x minus x, so that's a 2x, plus 2x, and plus 3. And in the denominator, we have an x minus 1, x plus 1, oops, missed a squared here, quantity squared. And as I mentioned in the first example, if we can factor what's left in the numerator, let's do it, just in case one of its factors cancels with one of the factors in the denominator. And in this case, x squared plus 2x plus 3 factors as x minus, oh no, it does not. So let's check. So the factors of 3 are, well, 3 and 1, and or negative 1, negative 3, and neither of those pairs add up to positive 2. So we're done. We can't factor the numerator. All right, let's do a few more examples. We have x plus 2 over x squared minus x minus 3x over 4 times quantity x minus 1 squared. So again, we have different denominators, so let's find an LCD. First step, let's factor the denominators. So the first denominator is x squared minus x, and we can factor it in this way. Each term in the first denominator is divisible by x, so we can factor out an x. And the second denominator is fully factored for us already. Nothing we can do. Okay, so now let's make a product in step 2. Let's make a product of all the factors that appear in either denominator. So in the first denominator, the factors that appear are x and x minus 1. And in the second denominator, the factors that appear are 4 and x minus 1. So all the factors that appear, the distinct factors that appear, so 4 appears, x appears, and x minus 1 appears. So we're not done. Let's look at each of these 3 factors, 4, x, and x minus 1, and raise each of them to the highest power that they appear in either denominator. So 4 appears 1 time in the second denominator, x appears 1 time in the first denominator, and x minus 1 appears 2 times in the second denominator. So in this case, the LCD is, in fact, the denominator of the second fraction. So when we go to change each of the fractions in the problem, we can actually leave the second fraction alone. Okay, so we're just going to change x plus 2 over x squared minus x. Let's write this as with a factor denominator, so that's x times x minus 1. Okay, and so the only thing it's missing, which factors of step 3 here is the denominator missing? Well, it's missing a 4, and it's missing a factor of x minus 1. Okay, so again, our denominator should be the LCD. And in the numerator, we are multiplying these two fractions. So we have 4 times x minus 1 times x plus 2. And because we're going to combine it with the other numerator, let's go ahead and simplify this. So this is 4 times x squared. Now we're foiling the last two binomials here. So we have x squared plus 2x minus x minus 2. Now, it's at this point that it's a common mistake is to notice that the numerator and denominator both have a 4, so we can just cancel them out, right? Well, no, because we want to keep it there so that we can combine it to the other fraction, right? So we don't want to cancel out. We just added terms to both the numerator and denominator. We added an x minus 1 term and a 4 term, I should say factor. We added a factor of 4 in the numerator and a factor of 4 in the denominator. We also multiplied a x minus 1 factor and a x minus 1 factor in the numerator and denominator. So we're going to leave them there. We're not going to cancel them out after we just put them there. So we're not going to cancel the 4's out. We put them there for a reason. So the numerator is now 4 times x squared. So 2x minus x is 1x minus 2. And here we still have 4x, x minus 1 squared. And we're going to go ahead and distribute the 4, completely simplify the numerator again because we're going to add it to the other numerator. So let's completely simplify it here. We can leave the denominator as is. Okay, so what we've done is we found the LCD, realized that the second fraction has as its denominator the LCD. So we only need to change the first fraction, and now we're ready to subtract. So this is just the original problem. Okay, so we changed the first fraction by multiplying it by 1, and the new first fraction is this. And we left the second fraction alone. Okay, so now we have the two fractions with the same denominator, so we can go ahead and perform the operation on their numerators. So we have 4x squared, still in the numerator. We have a positive 4x and a negative 3x, which just becomes x minus 8. Minus 1 squared. Okay, so let's see if we can factor the numerator. See if it will cancel with anything in the denominator. So the only hope the numerator has of canceling with anything in the denominator is if it has a factor of x minus 1. So let's see if the numerator can factor where one of the factors is x minus 1. If one of the factors is x minus 1, the other factor would have to be 4x plus 8, looking at the first and last terms here. So the first term is 4x squared. The last term is negative 8, so that checks out. Let's just check that the outer and inner, the sum of the outer and inner terms add up to 1x. So let's do outer. The outer would be 8x plus inner. The inner would be negative 4x. So this equals 4x, which is not equal to x. And so in other words, x minus 1 is not a factor of the numerator. So maybe the numerator does factor in another way, but even if it does, that's not a concern for us because it wouldn't be able to cancel with anything in the denominator anyway. 4 is not a factor of the numerator. X is not a factor of the numerator. And we just discovered that x minus 1 is not a factor of the numerator. So we're done. All right, let's do one more. All right, so again, we have a problem with two fractions whose denominators are not the same. So let's go right to finding an LCD. So step 1, let's factor each of the denominators. So the first denominator factors as x minus 2 times x minus 2, so x minus 2 squared. And the second, being a difference of squares, factors as x minus 2, x plus 2. Second step, list all the distinct factors that appear anywhere. So x minus 2 shows up in the first and in the second. And then we have an x plus 2 that appears in the second. And finally, so these are all the factors that appear anywhere. And finally, number 3, we're going to raise each of those factors from step 2, to the highest power where they appear anywhere. So the highest power that x minus 2 appears is in the first denominator, and it appears to a power of 2. And x plus 2 only appears in the second one, and it appears there one time, so we leave it alone. So number 3, here's our LCD. So it looks like we're going to have to change both fractions. The first fraction is missing. So this is the first fraction. I'm going to write it in the denominator in factored form. Is missing in x plus 2. And so we multiply the first fraction by 1, and we have 4x plus 8 in the numerator, and of course the LCD in the denominator. Again, we don't need to simplify this because we're just trying to get the denominators to look the same. We don't care what it looks like simplified. So that's the first fraction. Now the second one, which is x over x squared minus 4, or x over x minus 2 times x plus 2. What is it missing from the LCD? Well, it's missing a factor of x minus 2. Okay, so again, our denominator should be the LCD. And here in the numerator, we multiply and we have x squared minus 2x. Okay, so now that we've changed the two fractions, we're ready to combine them. So the original problem, we write down first. So it was 4 over x minus 2 squared plus x over x minus 2 x plus 2. So we change the first fraction to 4x plus 8 over x minus 2 squared times x plus 2. Wait, are we subtracting here? No, we're adding. Okay, plus. And we change the second fraction to x squared minus 2x in the numerator and the LCD that we found in the denominator. So again, we see that we have two fractions with the same denominator, so we can combine their numerators. And we have x squared. We have a positive 4x and a negative 2x. This is a 2x plus 8. Okay. Now let's see if we can factor the numerator. The only way it could factor is if any two factors of 8 add up to positive 2. So the factors of 8 are, well, 1 and 8, or negative 1, negative 8. Neither of those pairs add up to 2. And 2 and 4, or negative 2, negative 4. And again, neither of those pairs add up to positive 2. So we're done. Can't factor the numerator. Always check at the end of adding and subtracting rational expressions. When you get to the end, see if you can factor the numerator, because sometimes you can, and you can cancel with one of the factors in the denominator. You can simplify it even more. Okay. So that completes section P5. We learned how to simplify. Let's go to the top here. So we learned how to simplify or reduce rational expressions to their lowest terms. We factor both the numerator and denominator, and then cancel out any common factors. And we emphasize that we cancel out factors, not terms. And again, yeah, we emphasize this. So we looked at examples of the wrong way to cancel. Just to emphasize it one more time, because it's a very common mistake. Let's look at number 1 of a wrong way to cancel. What we did wrong is, even though there's an x squared in the numerator and an x squared in the denominator, x squared is a factor of the numerator, but x squared is a term of the denominator because it's being added in the denominator to everything else. So we can't cancel. We can only cancel two factors. In the second example, same thing. X plus 2, it is a factor of the numerator, but it's a term of the denominator, so we can't cancel the x plus 2's there. And again, x in number 3, x is a term of the numerator and it's a term of the denominator, so we cannot cancel. We can only cancel two things that are factors. Okay, and then we looked at how to multiply and divide rational expressions. We multiply rational expressions by first factoring them, factoring the numerators and the denominators. Then we multiply. We multiply the numerators, multiply the denominators, and then after we do that, we see if there's any factors that we can cancel. Now, I will point out, if we look at number 1, when we go to multiply these two expressions, we could have multiplied the polynomials as is, meaning we could have left it unfactored and multiplied x squared plus 3x plus 2 times 2x cubed plus 6x. We could have done that without factoring, but that would have been really messy, and it would have been very difficult to see that long expression, whatever you get, factors in this way. So we factor it first to save ourselves the headache, and then multiply the numerators here. And when we do that, notice we didn't simplify. So for example, we multiplied x plus 1 times x plus 2 times 2x times x squared plus 3, but we didn't FOIL, we didn't distribute. We left it as is to see if any of those factors canceled with the factors of the denominator. So don't do more work than you need to. Factor it, leave them in the numerator and denominator as factors, and then in the end see what you can cancel. Same thing with dividing. We talked about from quiz 1, the common mistake of distributing across multiplication. You can only distribute across addition. And today we learned how to add and subtract rational expressions by first finding an LCD. We talked about how to find an LCD. Talked about how to use the LCD to change each fraction. I wrote each twice. To change each fraction in the problem. And then combine them in the end.